So what would happen if everyone pointed a laser at the moon? First, we need to acknowledge this. Not everyone on the planet can observe the moon simultaneously. Theoretically, everyone could gather in one place, but we've experienced the consequences of that before. Most of humanity is located between the 0–120 degrees east meridians, so our best access to the moon occurs when it's positioned over the Arabian Sea. For the experiment, we'll choose the crescent phase visible from the night hemisphere, so we can observe the differences between the dark and light regions. Standard red laser pointers produce around 5 millidollars of power, and well-designed models have a beam concentrated enough to reach the moon, though it will be spread over a wide area when it gets there. We're assuming all participants can aim precisely and the light distributes homogeneously. The result, absolutely nothing. An expected outcome: solar radiation bombards the moon and Earth's surface with approximately 1 kilowatt of energy per square meter. Since the moon's cross-sectional area is on the order of 10 trillion square meters, the illuminated hemisphere receives about 6 petawatts of solar energy. Our collection of 5 millibar lasers across the entire planet, however, produces only about 30 megawatts of illumination in total. That is 200 million times weaker. It's physically impossible for us to detect the laser effect. What if we increase the power level? I understand. A 1W laser is an extraordinarily risky device. It doesn't just cause vision loss. It can burn skin tissue and ignite flammable materials. Lasers at this power level aren't strictly illegal, but restrictions have been placed on their sale in the US, which has led to the proliferation of suspicious $200 marketplace listings. 1-watt blue LED flashlight, highly focused beam, wink wink. I've personally examined a laser from such suspicious sources, and they're genuinely terrifying devices. You definitely shouldn't touch one without safety glasses that cost more than the device itself. Let's assume we spent $1 trillion budget to supply everyone with 1-watt lasers. The resulting effect? Impressive. This laser fleet is sending light to the moon's surface at roughly half a lux intensity. This value is equivalent to about half the brightness of moonlight as we perceive it on Earth. The 130,000 lux of radiation provided by the sun still completely masks the laser effect. What if we increase the power level? We need to temporarily move away from laser technology and distribute a night sun to each participant. The powerful searchlights used on law enforcement and Coast Guard helicopters. These devices, which output at the 50,000 lumen level, can instantly illuminate an area. Since the beam angle is several degrees wide, we need optical lenses to achieve the half-degree angle required to focus on the moon. It's hard to see with the naked eye, but we're making progress. Our total beam is producing 20 lux intensity and exceeds the natural light in the moon's dark region by a factor of 2. Still, it hasn't created a visible change in the bright hemisphere. What if we increase the power level? Well, let's replace each night sun with an IMAX cinema projector, a water-cooled dual lamp system at 30,000 W that produces over 1 million lumens. The effect is still at a minimal level. On the roof of the Luxor Hotel in Las Vegas sits one of the planet's most powerful searchlights. Let's add an optical lens to direct the beam at the moon, mount a color filter, and distribute one to everyone. There we go, our beam is now clearly visible. So we've reached our goal. Congratulations, team. What if we increase the power level? Okay, we need to return to laser technology. The Boeing WAL-1 was a massive laser system mounted in a 747 fuselage. Literally, it was a megawatt-class infrared laser integrated into a 747 aircraft as an experimental project of the US Department of Defense. Let's imagine we produce lasers in the visible spectrum with similar capacity and distribute them to everyone. We've finally reached a level equivalent to the intensity of solar radiation. At the same time, we're consuming 5 petawatts of energy, double the planet's average electricity usage. What if we increase the power level? Now let's place 1 megawatt laser on every square meter of the Asian continent. Operating this network of 50 trillion lasers burns through the planet's entire oil reserves in roughly 2 minutes. However, during those 2 minutes, the moon shines at the brightness of the late morning sun. By the end of the 2 minutes, the moon's surface regolith layer reaches glowing temperature. What if we increase the power level? We're now going way beyond realism, beyond even the levels we've reached so far. The most powerful laser on the planet is the confinement laser at the National Ignition Facility, a fusion research center. The system operates at 500 terawatt output in the ultraviolet wavelength, firing in pulse mode lasting several nanoseconds. The total energy transfer is equivalent to burning roughly 1/4 cup of gasoline. Let's assume we find a way to operate this system in continuous mode. We distribute one to everyone and direct them all at the moon. Unfortunately, the laser beams convert the atmosphere to a plasma phase and instantly ignite the planet's surface, killing all life. But let's accept that the lasers pass through the atmosphere without interacting. Even in this scenario, Earth still ignites. The radiation reflected from the moon is 4,000 times more intense than the midday sun. But let's set Earth aside. What's happening to the moon? The laser bombardment is transferring enough energy to vaporize a 2-meter thick layer of lunar rock per second. However, the vaporized rock particles don't disappear. Instead, the moon's surface layer rapidly transitions to a plasma phase, and this plasma layer blocks the incoming beam energy. As our laser continuously pumps energy into the plasma temperature rises exponentially, and the highest energy plasma particles shoot into space at incredible speeds. This flow of matter effectively turns the moon's entire surface into a rocket motor, and a surprisingly efficient one at that. The technique of launching surface material by blasting it with lasers is called laser ablation, and it's a promising method for spacecraft propulsion systems and moon propulsion. The moon has enormous mass, but is subjected to an extraordinarily powerful rock plasma jet. Rough calculations show the moon is pushed beyond laser range within a few months. During this time, the jet also scours Earth's surface and destroys the lasers, but we're assuming they're indestructible. The moon retains most of its mass, but escapes Earth's gravity and enters an unstable orbit around the sun. This deviant orbit is unstable in nature, and sooner or later the moon will either crash into the sun, be flung into the outer planetary system, or collide with a planet, most likely ours. I think we can all agree that in this case, we deserve our fate, and that's finally sufficient power